All right, so let's continue then our analysis of the effective rate of stop and wait when we now also allow for frame errors to occur. So we finished off last hour here by introducing the random variable nt, which is the number of transmissions needed to deliver a frame. So this is a random variable, and the probability that nt takes on the value I is pf to the power of I minus 1 times 1 minus pf. And this is defined for I equals 1, 2, 3, etc. This equality here is under the assumption that we have independent frame errors. Okay, which means that if we have just done a frame error, the next transmission will not be affected by that frame error itself. So, I mean, it's like if we lost a frame, the probability of losing the next frame doesn't change due to this fact. Okay, so independent frame errors with probability PF. Okay, so PF is the frame error probability. Okay, and then we can calculate the probability that we need one transmission, two transmissions, etc. Okay, what we are interested in is the average number of transmissions we need to do. The average number or expected value of nt, we can simply calculate that because we know the probability that nt takes on any specific value. So it's the sum from I equals 1, which is the smallest value nt can take on, until infinity, and then it's I times the probability that nt takes on the value I, which is pf raised to the power I minus 1 times 1 minus pf, like this. Okay, so this is the expected value of nt, the average number of transmissions required to deliver a frame. So this one looks complicated, but it's actually not. So if we just go through some standard, it's basically a geometric series. So we can calculate this, and we then at the end of the day we get this equal to 1 over 1 minus pf. For reasons which is not obvious now, we would be interested in the expected value of nt minus 1, okay, which is the expected value of nt minus 1. Okay, and by just putting in 1 over 1 minus pf minus 1, we see that this is pf divided by 1 minus pf. So simple calculations here. Okay. So armed with this knowledge, now let's calculate the time it takes to deliver a frame. Okay, so the time to deliver a frame for stop and wait is t subscript SW. Okay, so what can happen here? Well, if we have nt frames that we need to transmit, so we have nt minus 1 failures and then 1 successful. So the time it takes is the time it takes for the failures, which is nt minus 1. We have nt minus 1 successive failures, and all of these requires a time, namely the timeout time. Okay. So remember, when we send a frame, we start a timer, and after t out, it expires, and then we know something bad has happened, and then we retransmit the frame. Okay, so this is the time it is required for all the retransmissions, and then at the end we have 1 successful frame, and that takes TO, the reaction time. So if we don't have any failures, then nt is equal to 1, and the first term here disappears, and then the time to deliver a frame is t0, which we used in the calculation before. But for each error that we do, we increase the delivery time by t out, the timeout time. Question?
What was the index SV?
SV for stop and wait. Okay, so now we can actually calculate the expected time it takes to deliver a frame. So the expected value of TSW is the expected value of the random part, which is nt minus 1. And that should be then multiplied with the output time, and then plus t0. So let's put t0 at the beginning, and then we know that the expected value of nt minus 1, we just calculated that to be pf over 1 minus pf. So the second part is the timeout time times pf divided by 1 minus pf. Okay, so this is how far we get at the moment. So when picking the timeout, t out, what is a good value for that? Large, small? Depends, of course. And in this case, what would you pick the timeout to be? So let's go back to the timing diagram here. So we know that when we start to transmit the frame here, we start a timer also. When should the timer expire? You can say stop when it should expire. Stop. How about if it expires here? Or here rather. Here. Because if it expires here, that is the first time when we are sure that we would be able to receive an acknowledgement if it had been sent. If the timeout happens here, then we force a retransmission which is potentially unnecessary. If we wait too long, then we essentially waste time waiting for an acknowledgement that will never reach us anyways. Okay. So the best value of the timeout is this number here, okay, which is equal to t0, the reaction time. Okay, which is good because that would simplify this equation. So for t out equal t0, then of course the expected value of tsw then becomes t0 plus t0 times pf 1 minus pf, and we can just simplify that and we get t0 divided through by 1 minus pf is the end result. Just on simple manipulation. Yes. Okay, so now we can simply put all the pieces together. We know the average time it takes to deliver a frame is t0 divided by 1 minus pf. Remember, if pf is equal to 0, okay, so we make no frame errors, we expect this delivery time to be the same time as we had before, and it is indeed that case, because then it becomes just t0 as we had before. So it makes sense. However, if pf increases here, we see that the average time is also increasing. So when pf is approaching 1, that is, it's very likely that we do frame errors, the time to deliver a frame then increases also, and increases quite rapidly, right? Which is also to be expected. Okay, but we're interested in the effective rate here. So the effective rate for stop and wait, so RF, comma SW for stop and wait. It is as before, NF is the number of bits in the frame, and then we subtract off the overhead bits, check bits, headers, whatever. Then we get the number of bits in the service data unit, and then we divide through by the time it takes to deliver this. And since the time is random, we divide through by the expected value that, of the delivery time, which is the expected value of TSW. Okay. And since we know what this is, now we can write this as 1 minus PF times NF minus N0 divided by R. By T0, of course. And this latter part here, we recognize that as the effective rate when we have 0 errors. So the penalty for having frame errors is very neatly visible in this equation. So the effective rate we get is 1 minus PF, the effective rate when we had no errors. If we're interested in the efficiency of stop and wait, it follows from this that it's 1 minus PF times the efficiency. For stop and wait. For stop and wait when we have 0 errors. So it's actually a very simple equation, but to arrive to it was a little bit of some work required. So now we know the effective rate and the efficiency for stop and wait, and we see that it's proportional to 1 minus PF times the effective rate when we have no errors. So if we want to summarize, when is stop and wait good and when is it bad, right? So stop and wait is, let's concentrate on when it's bad. So it's inefficient when, okay. So what could make the efficiency low here? Well, of course, if we have a lot of frame errors, then that would cause a lot of errors. So but I guess that it's not so, that's expected, right? So when the layer below us is bad, then the performance that we can deliver is probably bad too. Another thing that makes this bad is when this delay bandwidth product, R times 2 Tprop plus Tpros, is much, much greater than NF. Then we're also in trouble. Okay. So this last equation came from the efficiency of stop and wait when we had 0 errors. So if we just go back to see where this comes from, it comes from the this term, right? So when the denominator of this fraction is larger, much larger than, if the numerator of this fraction is much larger than the denominator, this is large. And if this is large, then the effective rate or the efficiency is low. That should be clear. Okay. And the the culprit here, what is the root cause of this? The root cause of this is this period where the protocol, the transmitter in the protocol does nothing. Okay, it could have used this time to transmit more frames, right? So when we go to go back n, this is exactly what happens. So in go back n is the same, essentially the same receiver as before, but the transmitter is changed. So after transmitting this first frame, instead of waiting until it receives an acknowledgement of that frame, until it does anything else, it transmits the second frame here, if it has one frame to transmit, obviously, and then the third and the fourth, perhaps, and then it will process the acknowledgements as they arrive. Okay. So we can think of go back n as a number of parallel stop and waits. That's one way of viewing it. It's not a perfect analogy, but it's sort of what's going on. Or one can simply say that we transmit frames and we're optimistic that we will get an acknowledgement a little bit later, so we keep on sending frames. Okay? And when errors occur, then we have to handle them. Okay. Okay. So this is a summary slide of what we just did for stop and wait. So let's go and review what's happening when we do go back n. So here we have the transmitter and receiver, and we send the frame. Okay, just as we did in stop and wait, it will arrive at the receiver at some other later time, and then it sends an acknowledgement to this one. So here is the, I don't know, a blue frame, and then it sends an acknowledgement here, and the acknowledgement is in the form, in the following form. We request a purple frame, that's why it's purple here. But it's actually the acknowledgement of the frame that came before it, which is the blue frame here. Of course, the blue and the purple will be encoded into sequence numbers in a real, right? You don't send colored bits like that. No. Okay. So here's the simple transaction. So if this was stop and wait, we wouldn't do anything until we hit this time, and then we would send the next frame. But go back n, or we feel optimistic. So after sending the blue frame, we're optimistic that we would receive a request for the purple frame. So we send it before we get the request. And actually we send, once this goes over, then it requests the green frame. We guess that that would be the case. So we actually send the green frame here, and then we'll request the orange frame. And then we keep on going like this. Okay. Now, so everything works great here until we get an error. So what's going to happen when we get an error? Well, for each frame that we transmit, this frame, this frame, this frame, this frame, we will start a timeout. Okay? And the timeout now, we put that to be proportional to the frame duration. So it's this capital N times the frame duration. So what's going to happen then, if this frame is lost, then at this point in time, that would trigger a retransmission of that frame. So this we know. But the transmitter doesn't know at this point in time that this frame was lost. Actually, it will not learn that until at this point in time. So it happily keeps on transmitting frames here as if nothing bad has happened. However, these frames at the receiving end will be ignored because the receiver was expecting an orange frame, not the blue and not the purple one. So these would just be thrown away at the receiver, even though they might have arrived error-free, but they had the wrong sequence number. So then a timeout here would then cause the first retransmission, and that would be of the orange frame here. So that is then transmitted at this point in time. Now, the blue one here will also have a timeout that will hit, expires here, and then the blue frame will be retransmitted. The purple frame also has a timeout that will hit, will expire here, and that will be retransmitted. Okay. So even though just a single frame error occurred, that triggers a number of retransmissions, namely capital N number of frames. How many frames? Well, it depends on how we have selected the timeout, and it's selected to be N times TF. So if we pick N large here, it's going to be a lot of retransmissions. If we pick N small, it's going to be fewer retransmissions. But again, we cannot make the timeout too small. It has to be larger than the turnaround time. Otherwise, we will trigger unnecessary retransmissions. Clear? Okay. So, and then we keep on sending ACKs and so forth. So let's just, I'm sorry for this. So I'll stop. Okay. Okay, so here's the whole diagram now. But the important thing is that one frame error causes N retransmissions. So now when we want to do the efficiency analysis for go back N, we see that efficiency when we have no errors is very good, right? For each TF second, we can transmit a frame and we receive a frame every TF seconds. So this is the best we can ever hope for. So it's very good protocol as long as we don't have errors. However, when we have an error, it causes retransmissions not only of the frame that was in error, but also a number of frames that comes afterwards, even though they were delivered without errors, because these will be ignored by the receiver. Okay? So we can sort of intuitively already now see that go back N will have excellent performance when there is few or no errors. However, it's sort of also reasonable to think if we have a high error probability, then this will perform poorly. Okay, so let's and this is true. So let's quantify that. Okay, so we know that stop and wait is inefficient like this. So let's go and talk about go back N. Okay, so for highest efficiency or effective rate, what we want to do is to make sure that if the channel is idle and we have data to transmit, we do transmit. Okay, so we make the send window large. Okay. So the send window times the frame duration, okay, should be larger than the reaction time. If that is true, then we can always send, the idle time, so we would never wait, the transmitter would never be idle, it can always transmit the frame. Okay. So it will never stop sending frames because it doesn't have any frames to send. Okay. For simplicity, we say that WS is then equal to T0 divided by TF. And we assume that this is an integer, otherwise we need to round that up. But let's assume that this is an integer. And this timeout, if we take the timeout equal to T0, then that implies that N is equal to WS, the send window, which is the time, the reaction time divided by TF. Okay, so this is typically what we would like to do. We put the timeout to be slightly longer than the reaction time, just as we did in stop and wait, and we make sure that we have enough space in the send window to keep the channel busy. Okay. What makes this difficult now, go back-end analysis, is that we have these retransmissions that depends not only on the frame that you're interested in, but also what happened to frames before it. Okay. So to make things simplified here, we do a simplified analysis, which turns out to be reasonably accurate. So we consider the transmission of the first frame. So think of this as that we are powering up our everything, and then we need to send the first frame in a go back and ARQ protocol. And since there were no previous frames, there are no errors in those frames that could affect how many times I need to transmit this first frame. Okay. So the first frame is not affected by any previous frame errors. Simply because there are no previous frames to be transmitted. Okay. Okay, and then we introduce NT, and here it has the same interpretation as before, except now, to be a little bit more precise, is the number of transmissions needed, to deliver the first frame. Okay, so it's the first frame, not any frame. It's the first frame that we look at. Okay. So how many times do we need to transmit the first frame before it's delivered? Okay. The total number of transmitted frames needed before the first frame is delivered. What is that? Well, first of all, it's 1, because it has to be successful, right? And then for each failure, how many failures do we have? We have NT minus 1 failures of the first frame. For each of those frames, frame errors, we trigger a retransmission of the first frame and also some other frames, right? The adjacent frames. So in total, each frame error causes capital N retransmissions. Okay. I'll quickly go back to the keynote here. Yeah. So this frame error causes a retransmission of that frame, but it also causes retransmission of 2 more frames here. In total, for each failure, we get N frames that we need to retransmit or transmit. Okay. So the total number of frames, not only the first frame, is 1 plus NT minus 1 times N. We cool with that? Okay. Time to delivery. T with subscript G, B, N, go back N, is then TF, the time it takes to transmit 1 frame, multiplied with the number of frame transmissions, which was 1 plus NT minus 1 times N, capital N, like this. Okay, and then we take the expected value of this. And then, as before, we have TF 1 plus the expected value of nt minus 1 times capital N, like this. We know that the expected value of nt minus 1, assuming independent frame errors with probability pf per frame. So this is simply equal to pf divided through by 1 minus pf, like this. And after some calculations here, one can show that, and I think you should do this at home to ensure yourself that you understand what's going on here, is TF times the ratio 1 minus PF times capital N minus 1 divided through by 1 minus PF. It's just some simple algebra. Okay, and then the effective rate for go back N is again the number of bits in the service data unit, which is NF, and subtract off the overhead bits, and then divided through by the average delivery time, which is the expected value of TGBN, like this. And then there is some routine algebra, and at the end of the day, it's capital R times 1 minus PF times 1 minus N0 divided by NF divided by 1 plus PF N minus 1, like this. Okay, and everything that multiplies R here is the efficiency for go back N. Okay, so if we then look at the efficiency here, when is the efficiency low? Well, the efficiency is low when we have a lot of frame errors, same as we had in stop and wait. Okay, seems like we cannot do much about that. But then we have another fraction here. So N naught divided by NF is the overhead due to the protocol, same as we had in stop and wait. But then we have another denominator. We have 1 plus PF times N minus 1. So if N, so what is N here? Well, N has to do with the N here. We know that N is T0 divided by TF. So we can make a further simplification of this to figure out what is causing what N is here. But essentially what we can see here, it has to do with the reaction time, which is given by propagation times and so forth, divided through by the frame duration. So let's do a simplification here, that N is equal to T0 divided by TF. And if we want to write that in terms of the rate, R, okay, so TF is R divided by NF. So here we have T0 by NF, like this. So the effective rate for go back N can be written as R times 1 minus PF times this fraction 1 minus N0 divided by NF, and then divide through by 1 plus PF. And then capital N, we replace that by R T0 divided by NF. Sorry, should be small nf, and then subtract off 1, like this. Okay. Now, if we have a very low probability for frame error, then the effective rate of go back n is r times 1 minus n0 over nf. Okay, and this is the best we can hope for. By any protocol. And the reason why this is the best we can hope for is that R is what is the rate below me, and I can't improve on that. And then here is just a term which penalizes me for adding some overhead bits to the service data unit. So of course we can make sure that the overhead bits are as few as possible, but it's, you know, it's limited to what we can do. So this is the best we can hope for. But when the frame error probability becomes larger, then the efficiency of go back n degrades rapidly, and very soon it's no better than stop and wait. Okay. So the efficiency decreases and approaches the efficiency for stop and wait. Okay. So if we have a lot of errors, it's not meaningful to go back n, because we can just as well stick with stop and wait. Okay. So what should we do then if we have a situation where stop and wait is not efficient? Okay, which could be due to this long reaction time, delay bandwidth product, which is go back n is not sensitive to this. However, go back n is sensitive then to frame errors. So what we need to do then is to find a third protocol which is not so sensitive to frame errors. And it's actually not so difficult to figure out what that should be. The main problem here with go back n is that perfectly good frames are ignored by the receiver because they don't have the right sequence number. So if we have a receiver that can buffer these until it receives a perfectly good orange frame, then we don't need to retransmit the purple and blue frames here. So basically what we do is that we have a buffer also at the receiver that can buffer frames which are out of order but otherwise perfectly good. Okay. And that's exactly what we do in what's known as a selective repeat. So a selective repeat receiver, what it does is that it has a receive window in which it stores previously received service data units which are error-free, but not necessarily in order. So there might be an out of order reception here. So we have received 0 and 1. 0 and 1 has been delivered, but we're still lacking 2 here. But we received 3 and 4 in the meantime, and actually 6 also. So the next time we get a service data unit at the receiver, maybe this is service data unit 2, And then we can deliver 2, 3, and 4 to the layer above us. Okay, and then we can slide the window to start here, and then we are waiting for 5, 6, 7, and 8, and so forth. Okay, so selective repeat is essentially to introduce a buffer at the receiver, and then the receiver constantly asks for the oldest not yet received frame in the window, and once it gets that, then it can deliver that and any other frames which have already been delivered to its layer above it, and then this will be then the next frame that we're waiting for. So I hope the principle is pretty clear here, and one can show then that this one, selective repeat, performs as go back n when there are no errors, because it's essentially go back n when there is no errors. When there are errors, then it handles these errors more gracefully than go back n, simply because it can buffer already correct frames that are received in out of sequence. So selective repeat is what performs the best here. So if we just want to summarize here, stop and wait, simple protocol, it's used, and it's used when the delays are not too long, the delay bandwidth product is small, and when the delay bandwidth product becomes larger, we go back n, because that handles that situation better. But if there on top of that starts to become errors, frame errors are prevalent, then we go to selective repeat. So TCP, for instance, uses selective repeat, because that's a good fit for that. But for some lower layer protocols, go back n and stop and wait are quite common. So all are used. Okay, so that ends today. And let me just remind you, there are guest lectures on Monday. Please go and see them. You will be exposed to experts in the field. It will help you select also your project. We will send out an email to explain when the sign up for the project topics are released.
Is there an exercise on Thursday next week?
Can't recall. I think so. So check ping pong. Is there 1 or 2 exercises?
I think there would be 2, one for the project.
Yeah.
I mean, one would be dedicated for questions about the project, and the second would be standard.
Yeah. So check ping pong or time edit.